so now we're going to look at the de Broglie equation. And let me first apologize to anybody who might be French speakers. I'm quite sure I just destroyed this guy's name. So let me apologize in advance. All right, so let's talk about this equation. Now, this equation came about because de Broglie speculated that matter can behave as both particle and waves, just like light or radiation. Ordinary radiation can have some particle behavior as well as wave-like behavior. So what de Broglie suggested is that if you have any object that is material and if it's moving, then not only is it moving like an object, particle, whatever, but also will have a waveform associated with it. So he did some theoretical work and he came up with this equation right here, which relates the wavelength of associated with a moving particle and the velocity, right? So lambda is the wavelength, h is the Planck's constant we met before, m is the mass, and nu here, or actually v here, would be the velocity. And in terms of the units associated with each of these terms, the units of h is joules second. The unit of mass here is kilograms, and the unit of velocity here is meters second. Now, one thing you need to remember, and I think we mentioned this before, is that the joule unit is the same thing as, let me write it up here. Whoops, hold on, where is that thing? Okay, where is it? The joule unit is the same thing as kilograms meter squared over second squared. So if we put all this here where the joule is here, then what will result is that the wavelength units will be in meters. All right? Okay, so based on that equation, you can calculate the wavelength of any, or the wavelength associated with any moving particle. And this is one of those examples where somebody's theoretical work ultimately led to the development of something useful to mankind, so to speak, applying science so that technological developments would result in, certain advances, such as in this case, in the case of the de Broglie equation, his theory led to the development of the most powerful microscope that exists, and that's the electron microscope, where a stream of electrons is used instead of light in order to reveal, smaller particles, bacteria, whatever. All right, so this is an example where science leads to technology, which leads to a very important invention. All right, so another person that came into action during this time is this guy, Werner Heisenberg. And he came up with his uncertainty principle, which states that we can't know simultaneously where a tiny particle like an electron is and exactly how it is moving. And there's an equation which basically summarizes this, which we won't get into right now. But the important thing that you need to recognize is that the act of measuring a particle actually interferes with the particle. And that is the reason why you cannot know exactly where a tiny particle is and how it is moving. So just to illustrate this whole idea of the uncertainty principle, let's say you have an electron, and let's say you have a special microscope that can actually visualize the electron if you look through it. But in order for you to see the electron, you need a photon of light to bounce off the electron and head towards the microscope. But when that happens, the state of the electron will be somewhere else. And by the time the photon hits the microscope here, you'll be seeing where the electron was at that instant and not where it is, which would be down here. So basically, that's the reason why it is impossible to tell how the electron is moving and where it is at the same time. And based on this uncertainty principle, that led to the failure of the Bohr model, which we were talking about. The Bohr model works well, but because of the uncertainty principle, we cannot tell where the electrons would be, and therefore the Bohr model will suggest that we can tell where the electrons are and how they're moving in orbits. Turns out not to be true, all right? So even though the Bohr model works well for hydrogen atoms, it is shown not to be a true representative of how the electrons are behaving and moving in an atom. So the point being made here is what I said before. When the photon is detected after bouncing off the electrons, the electron is in a different state, and therefore what you see at that instant is not exactly what is in terms of the position of the electron. Okay, so this leads us now to the area that leads to the current understanding of the electron's arrangement in atoms, and that is quantum mechanics, which is also known as wave mechanics. And basically the treatment that is involved here is the electron properties being displayed or treated as a wave-like behavior. All right, that's the type of behavior that electrons will display. And this guy, a German by the name of Erwin Schrodinger, he developed an equation that is used to describe the behavior of electrons in an atom. Now, I will not show you that equation because it's a rather complex equation. And basically, the only thing I will say about the equation is that you can find what is called a solution to this equation, which is called a wave function. And the wave function basically represents the energy state of the atom. In fact, the wave function is basically correlated to the orbits in the Bohr model, which of course we said we now know not to be a true representation of how the electrons are arranged in the atom. All right? So that's one important development which leads to our current understanding of how the electrons are arranged. Because wave mechanics, the approach taken by Schrodinger, provides a different measure. It doesn't say anything about absolute certainty of where an electron is, but instead it provides a probability of where an electron will be in certain regions of the atom. And according to Born, the way we interpret the wave function is that the square of the wave function is what actually gives us the probability of finding the electron in a small volume of space around the atom. So this leads to an idea of a cloud of electron density, which is basically a region in space where the probability of finding an electron is relatively high, rather than electrons basically following elliptical paths around the nucleus. All right? So it's that's basically our current understanding of how the electrons are arranged in an atom. We cannot say with absolute certainty where the electron will be at a certain point. Instead, the best we can do is talk about the probability of finding an electron within a certain region. Okay, we're going to stop here. The next topic we're going to talk about is and related to what we just discussed. We're going to talk about quantum numbers and atomic orbitals. All right? Until next time.